Welcome in, everybody. Yeah, I think we're good. Any questions before we get started? Anybody have anything they want to ask before we get going with stuff? Looks like people are, by and large, almost all of you are doing quite well on the homework and moving along at a steady pace. So I think we are ready to transition into graphs and linear equations and that kind of stuff. So let's do that. And I don't see any questions. Feel free to ask questions if you have any. Right, throw them in chat or raise your hand and ask with audio or however you want to do that. Ask me a question and we'll move ahead. Otherwise, I'll just kind of take a look at some things that you're going to be working on. So kind of getting into chapter 3, linear equations and inequalities with two variables. Excuse me. Still a little congested from my cold that I had. So this is a little bit different, but we're going to be using the same basic tools that we used before for linear equations, but in one variable, but we will be expanding on those. So remember when we did linear equations in one variable, that would be equations we did that were like 2x plus 1 equals 5 or something. And then you would, you'd use the addition rule to get the variable term on one side, the constant term on the other, and then you would divide both sides by the coefficient, and then you'd solve the variable, right? We're going to be using those same tools. So that addition rule and the multiplication rule that I just talked about, you're still going to use those. But we have to interpret things differently now because now we have linear equations in two variables. And at first, it's easy to go, well, what does that even mean? There's two variables. What does that represent? And one way of interpreting it is dimensions, right? So when we had linear equations in one variable, you could sort of think of that as all happening on a number line, like one dimension, just a line, right? Well, now we're going to have two variables. So things are going to be in two dimensions, like a piece of paper, two-dimensional. You've got length and width. So now we're going to have an x and a y axis. And we're going to go through. I'll show you everything about what that means. Well, I won't have time to show you everything, but I'll show you some stuff. And then hopefully between that and then the Delta Math videos, you'll start to piece it together and kind of understand what's going on there. So I'll give you the quick rundown here. For those of you who, I know some of you have seen this before, some people have not. So we'll just do well, you definitely should have seen some of this before. So I'll do a fairly quick run through. And like I say, hopefully if you come to office hours or you watch the Delta Math videos or something, it should fill in anything that you're missing or don't remember. So what we start off with here is an equation. Let me see if I can fit this here a little better. We have an equation in two variables. So let's take, for example, 2x plus 3y equals 6. Is that big enough? I think that's showing through on the screen big enough. 2x plus 3y equals 6. What do we have there? We have an equation. There are two variables. There is an x variable and there is a y variable. And then we have an equation, right? They're sitting inside of an equation. And somehow we have this line over here that somehow is connected to this equation. So what is that? How do I go from having an algebraic text equation to now I have a line appearing over here? How are those things connected to each other? Well, let's just take half a step back and just remind ourselves. Here's our two dimensions I was talking about. We've got a horizontal dimension and a vertical dimension, right? So usually, this isn't always the case, but most of the time, if you're given something with x and y, you just assume that the horizontal is your x variable and the vertical is your y variable. Sometimes you might have completely different variables in your equation. You might have revenue and cost. In that case, you might have R and C as your variables, and then you'd have to figure out, well, maybe my revenue is horizontal and my cost is vertical. That's kind of down the road. For now, we're mostly going to be dealing with x and y when we're graphing. So you should just think x is horizontal, y is vertical. So whenever we think about the x variable, we're thinking about moving left and right. When we think about the y variable, we're thinking about moving up and down. Okay, so this point in the middle is called the origin. And if you want to move to a different point, there's two things you need to know. You need to know how to move left and right, and you need to know how to move up and down. So what happens is we take a point and we put two components in there. Let's say 4, 2. So how did this pop up? Well, if you start at the origin, the first component is horizontal. It says to move 4 in the horizontal positive direction and 2 in the vertical positive direction. Okay? So that's how we get 4, 2. You go over 4, up 2. What if we have negatives in here? Well, that's... Oh, I should move this up so you can see it a little better. What if we had negatives? Well, I can make that -4. And what did that do? That meant we moved 4 horizontally in the negative direction and then up 2. What if I made that -4, -2? That means you go 4 in the negative horizontal direction, 2 in the negative vertical direction, and you get your point right there, right? So, so there it is. Okay, so there you've got your points. So let's go back to the line. Okay, so actually, we see this as a straight line, and people think of this as like a bar or some kind of physical object that's like solid, right? It looks like a solid bar, like a, some kind of a bar that you'd use for a pole or a, pull-up bar, some kind of a thing where it's just like a long cylinder or something. It's actually not. This graph is really a bunch of individual points, right? All really, really infinitely close together. And each of those points represents a solution to this equation right here. So if you can take an x and a y value and plug them into this equation and it gives you a true statement, that's one of these points. That's what the line of an equation is it represents the solutions to these equations right here, to this equation right here. So let's look at a table. Let's make a table here, and let's kind of pick some that seem like they would satisfy this. In fact, let's move this over so I'm not blocking it. We'll put it right there. Okay, so what if I picked, what's an x value I could pick? Well, I could pick 3 for my x value, right? So if I plugged 3 in here, that would be 2 times 3 was 6. Well, that would mean that my y is 0, right? So if I plug in 3 for x and 0 for y, I get 6 equals 6. That's a true statement. Notice how that became a point on my line, right? What if I try something that doesn't work? What if I go 3, oh, oops, that's not a 3, is it? 3 and 3. That doesn't work, right? Because notice that if I plug that 3 in for x and 3 in for y, I get 6 plus 9 equals 6. No, that's not true. And notice how the point does not lie on our line, right? So combinations of x's and y's that fit this equation are points on the line. Combinations of x and y's that don't fit this equation are points off the line. They are not on the line. They are separate. See how that works? Okay, so this can work both ways. And as you progress through your math classes, you're going to be doing that a lot. You're going to be switching back and forth, going one direction to the other, especially those of you who are going the calculus route. So you're taking either college algebra or pre-calculus or something along those lines. You're going to sometimes have a problem where you're looking at a graph and you have to turn everything into algebra. And then you're going to have times where you have a bunch of algebra and you have to turn everything into a graph. So you kind of want to get to a point where you just see them as different representations of the same thing, right? Where they look different, but they're the same thing, right? And you can understand how they're the same thing. So we can see them in the algebraic equation form, and we go, yeah, I understand how that works. And then we see them in the graph form, and we go, yeah, okay, I know how that works, right? Kind of like if you've got like, if you've ever seen like where you're taking a picture of something and the lighting is all coming from the backside, and so you have to light the front. So you take a picture of your friends, and you've got the front view, and here's a good picture of my friends. And then you turn the light off, and everything's backlit, so you're just seeing them. You're seeing like silhouettes, but you still can recognize like, oh, I know who that is on the left. I know who that is on the right. Even though it looks very different, you still can interpret what you're seeing, right? That's what we want to do here. We want to be able to look at the algebra and interpret what we're seeing. We want to be able to look at the graph and interpret what we're seeing. If you can't do that, like it takes a little bit of work now to get comfortable with that, but it's going to pay off through all your math classes that you have to take from here on out. Even if you're not taking the classes I just mentioned a moment ago, Even if you're going into statistics, lines are a big deal in statistics, right? Because you're going to find this thing called the line of best fit. You want to know how to graph those, all that kind of stuff. You got to know how to do this stuff. So any math class, whatever math class you're going into the future, you want to be real comfortable with lines and switching back and forth between the algebra and the graph, right? That's actually a common thing I see. I teach stats all the time. I'm teaching 3 stats classes this semester. Students they're like, oh, well, I don't remember how to do lines because that was back in algebra. Why do I still need that? Well, because we use lines in statistics. So you kind of need to know how to graph a line if you're going to be in statistics, right? So you want to get comfortable with that. So this works both ways, right? I picked a point. I picked an X and a Y that I knew worked. And when we graphed it, it ended up on the line. But we can go the other direction as well. What if I take a point on the line and then use that to plug it into the equation? Yeah, that works. That's what I'm talking about, being able to switch back and forth both ways with the graph and the algebra. It's helpful. So like, let's take a point here. How about 0, 2? Okay, so that's the point we're talking about, 0, 2. Oops. There we go. See how that's a point on the line? Also, if I plug in 0 for X and 2 for Y, I get 6 equals 6. Yeah, that works. Okay. Just remember, the first component's always X. Second component is always Y. So you're going to learn a couple of different ways of graphing lines. You might go, why do I need to learn a different ways of doing the same thing? Well, the first way we're going to learn, you can graph anything. Lines, parabolas, ellipses, really fancy things, but it's kind of tedious. It can take like if you're going to graph an ellipse by plotting points, which is what we're about to do, you might have to plot 100 points, right? That's a lot. I don't want to plot 100 points. Who wants to do that, right? So that's why we generally have some basic ways of graphing for when you're stuck or when you need to like supplement your other ways. But we also want to learn these fancier ways of graphing lines that you'll learn from watching the videos and, the videos that are in Canvas and the videos on Delta Math and that kind of stuff for making sense of these things, okay? So let me catch my place. Whoops, this is not the one I wanted. Kind of lost my place for a second. Where am I? Graphing linear. Yeah, right. Okay, so that's kind of how a graph works. Let's look at a couple problems. So let's go to graph stories. This is really important. A lot of times people want to skip these and go, I don't like word problems. Let's skip this. Word problems are like the most important thing because outside of the classroom, any math you run across in life is some type of word problem, right? It's not like you're just walking along the street and you find an equation and decide, oh, I'm going to solve this equation. That never happens, right? What happens is you're taking out a loan for a house or a car, or you're trying to plan for retirement, or you're trying to do that. And what you have is a whole bunch of information, and you have to gather that information and then do some calculations on it. It's a word problem. It's a real life word problem. So if I hear this from students, they're like, I can do math, I just can't do word problems. Then you can't do math. It's the same with fractions. I can do math, I just can't do fractions. Then you can't do math, basically, because in the real world, almost everything involves things that are not necessarily integers, and they involve having to put together what is essentially a word problem, right? So if you don't master those, essentially you won't ever use math in your life, and that's rough because as every math professor in the department will tell you, we've all had the experience of going in and trying to buy a car, and they give us a loan offer, and you just sort of laugh in their face. No, we won't be doing that. And then, you get to a better place. You negotiate to a better place. But a lot of people that don't know math, they just go in, and the car dealership says, here's your offer for your car loan. And they just go, okay, I'll sign it. Those people are losing a lot of money because they don't know the mathematics and how to process the mathematics of realizing I just signed up for a bad deal, right? We literally did this in one of my classes once where it wasn't an algebra class. It was what was called I think it was called Math for Life something. I forget what it was, but it was a topics course. And one of the students, she literally did a project. Her presentation was about realizing using financial mathematics to realize how bad her loan was that she signed up for. She refinanced it. She was saving like $250 a month. Same car, just got a better deal because she understood how much she was overpaying before. So I know there's a tendency for people to think they don't really need math in their life. People who don't have much math skills end up giving away a lot of money to people who want that money. Car dealerships and people who sell you your home and all sorts of stuff. Not as prepared for retirement because you're not, you don't really know how to prepare for retirement because you can't crunch the numbers. So all this stuff's really important. So you have to understand word problems and you have to understand how to put things in a graph so you can interpret them. So let's look at a problem here. Okay, here's a big one. And it's good. This is good. With these big problems, they really help you sort of think through. Wait, did we do this already or was that the other class? I don't think we did them yet in here. Let me know if we did this already, but I don't think we did. I think that was in my Math 3 class where we covered this already. So you just want to break it down bit by bit and make sense of it. Okay, so if you just read this whole thing beginning to end, it's not going to make any sense, right? Like I'll do that just as an example. Cameron left his house at time 0 and drove for 2 minutes to the store at a speed of 3 blocks per minute. Then he stopped and went into the store for 7 minutes. From there, he drove in the same direction at a speed of 2 blocks per minute until he got to the bank, which is 6 blocks away from the store. He stopped at the bank for 6 minutes. Then he drove home at a speed of 6 blocks per minute. Make a graph of showing the number of blocks away from the home that Cameron is X minutes after he leaves his house until he gets back home. Now ask me a question about that. I can't answer anything. I don't know, because I just went through and I tried to digest that entire paragraph at once. I literally have no idea what I just read, right? Because you can't do that with mathematics. And I see students do this all the time. They start at the beginning, they read to the end and go, I wonder why I don't understand it. Because you can't do math that way, right? You can't, like in a history book or a history class, you can sit down and you can read a chapter on history that's maybe like, Reconstruction, right, after the Civil War. And it's laid out like a narrative. You read it like you're reading a novel. And you go, okay, here's this paragraph's about this part of Reconstruction. And then they did this. And then they were, trying to build things. And it makes sense. Mathematics, you can't read it the same way. You can't sit down and just read a math book like you would a novel. You have to break it down into little pieces that make sense. Then move on to the next piece. Make sense of that. Move on to the next piece. Make sense of that. So here, let's break it down. And we'll see how much more this makes sense to us. Okay, Cameron left his house at time 0 and drove for 2 minutes to the store at a speed of 3 blocks per minute. All right, that's one sentence, and there's already a bunch of information. There's like 3 different pieces of information in just that one sentence. Okay, so I wonder if I can make this a little smaller. Let's do this. I'm going to try to fit it all on there at once so we can see the whole thing. There we go. Okay, got it all there. Okay, so let's just make sense of this. Cameron left his house. Oh, and by the way, let's figure out what we're doing. At the bottom it says, make a graph of showing the number of blocks away from home that Cameron is X minutes after he leaves his house until he gets back. Okay, first thing you always want to do, make sense of your graph. What does it represent? Like read it and go, okay, let's see. My x-axis is time in minutes. Okay, so I know anything that has to do with minutes, that's going to be left and right information. That's horizontal information is minutes. That's great because up here it'll say minutes on it. This is why a lot of people like to lose units. They just stop using them. The science teachers kind of complain sometimes that they're like, oh, when your people get out of your algebra classes, you never teach them to use units. We teach them to use units. People don't want to use units. It's actually way to your benefit to use units. You'll make less mistakes and stuff will make more sense. So think about the unit that you're using. Right here, I know anything I read in here that says minute, I know I'm going to be thinking about the x-axis. Look at our y-axis. It's distance, blocks from the home. So anything that talks about blocks, oh, that's vertical information. So right now, if you come to me and you say 7 minutes, I know, okay, that's horizontal. You say 4 blocks, okay, that's vertical. So see how I can already direct that information to where it's supposed to go? I can narrow it down. this is what you want to do when you see a graph. You want to make sense of it and go, okay, I understand what's going on here. Okay, so we want to graph how far Cameron is away from his home at any given time. And we have time on the x-axis, distance on the y. Okay, let's go back and start over. Cameron left his house at time 0. Okay, so if he's at his house at time 0, that means we should have a point here, 0, 0. So what I'm going to do is click right here and see how it starts to lay down a line for me, and I can complete it anywhere I want. Where should I complete it? Well, let's see. Cameron left his house at time 0 and drove for 2 minutes to the store. Okay, so 2 minutes, that's time. So I know my next point is going to be at x equals 2. So it's going to be somewhere where x equals 2, somewhere on here. I don't know where yet, but somewhere over there. Okay, at a speed of 3 blocks per minute. So notice they didn't give us all the information. They didn't say after 2 minutes he was 6 blocks from his home. They didn't say that, right? We have to figure that out. We have to fill in the gaps. This is that critical thinking piece. This is the thing that actually makes a person good at math and able to make good life decisions based on mathematics, is filling in the gaps of the information that you have. Okay, well, if he was driving at a speed of 3 blocks per minute for 2 blocks, then how many blocks did he get? 6 blocks, right? If you drive 100 miles an hour for 2 hours, how far have you gone? 200 miles, right? If you drive 3 blocks per minute for 2 minutes, you've traveled 6 blocks. So that means that after 2 minutes, he's gone 6 blocks. So I put my dot there, okay? Now that's just step 1. We're going to add more points. But look, we got sentence 1 taken care of. We're done. Sentence 1 is good. Okay, let's move on. Then he stopped and went into the store for 7 minutes. Okay, so 7 minutes occurred. So that's going to take us from 2 to 9, right? From 2 to 9. Our next line on the x-axis will start at x equals 2, and it will end at x equals 9. But what about my vertical? What am I missing here? He stopped and went into the store for 7 minutes. Okay, well, for the 7 minutes that he was in the store, did his distance from home change? I mean, you could argue that the back of the store is 100 feet farther away than the front of the store, but we're talking about blocks from home. While he was in the store, did he increase or decrease his number of blocks away from home? No, it stayed the same. So while we had a change of 7 minutes, that's the x-axis, we had no change in blocks, that's the y-axis. So that tells us that this part should go from 2.6 to 9.6. And these graphs are kind of small. You got to make sure you lined them up right. Okay, looks like I got that. Okay, does everyone understand the horizontal? There was no change in the number of blocks. That's what this represents. There's no change in the vertical. Or horizontal changed because the time changed while he was in the store, but his distance from home did not change. See how that works? Feel free to ask questions if you have any. Okay. What do we have? From there, he drove in the same direction, so he's still going away from home, in the same direction at a speed of 2 blocks per minute until he got to the bank, which is 6 blocks from the store. So again, a bunch of information in that paragraph. Let's think about that. Okay. He traveled 6 blocks, and he did it at 2 blocks per minute. So how long was he driving? 3 minutes, right? How long would it take you to go 6 blocks? If you were going 2 blocks per minute, it would take you 3 minutes. So that means that from there he drove in the same direction, 2 blocks per minute. So, okay, so we have 3 minutes, we said. So we're going to start here and go over 1, 2, 3, and then he covered 6 blocks. So 1, 2, 3, 4, 5, 6, and I put my point down. Do you see how this graph is starting to represent the story that we're covering? Right? If you can do this, if you sit down and work your way through a few of these problems, you will get good at understanding graphs. They will help you. And understanding graphs is just hugely helpful, right? Okay, where are we? He stopped at the bank for 6 minutes. Okay, if he stopped, again, remember his distance isn't changing, but he's sitting there for 6 minutes. So 1, 2, 3, 4, 5, 6. So the y value is not changing, but time is changing. Then he drove home at a speed of 6 blocks every minute. Ooh, he's going much faster on the way home. Maybe taking the freeway home or something. So then he drove home at a speed of 6 blocks per minute. So you could do this a couple ways. There's more than one right way to do this problem, okay? Everyone's graph will look the same, except you might have more points in here. So you could do it this way. You could say, okay, if he's covering 6 blocks in a minute, that means I go over 1. But remember, his direction has changed. He's going home now. So his number of blocks from home is decreasing because he's driving back home. So then I'd go down 1, 2, 3, 4, 5, 6. And then I'd go over 1, down 1, 2, 3, 4, 5, 6, and put it there. That's fine how I have this in 2 segments, or you can just do it in 1 segment where you go right from here to there. Assuming I did that right. So it's down 12 and over 2, right? Either one of those will be marked correct. So now I'm going to submit my answer. It says, are you really sure? I think I'm pretty sure. And I got it. All right, I got it. So see, and then what it does, it breaks it down for you. So you can see in the solution they give you the color coordinated pieces. So they see the red one. They talk about the red. Wait, where's the red piece? Oh, red they just have right here. It's harder to see. It's red. But your start, then you've got your yellow, your green. They explain the green, your blue, your purple, right? So you can see how each piece fits that story. So that's what you're going to do. And along the way, you're going to have a couple calculations. They don't always tell you exactly what each point is. You just got to, you got to fill in the gaps, just like in real life. People aren't going to hand you complete information. You got to fill it in. Partly, they don't give you complete information because they want you to sign the loan they want to give you. Right. This is typical. You can actually go online. You can research the mathematical tricks that car salesmen use in order to sell you vehicles. And that if you're not sharp with your math, they will confuse you, and you'll end up signing something that later you go, oh, I thought I was getting a better deal than this. Okay, let's do this one. What is this? Okay, now we have interpreting a graph story. So now you're doing it differently. You created the graph a moment ago. Now what you're going to be doing is looking at a graph and understanding what it means, right? So it's kind of the opposite direction of what we just did. During a snowstorm, snow fell at a constant rate for a number of hours. Then it stopped snowing for a number of hours. Then it started up again at a different constant rate. Damien made a graph showing the inches of snow on the ground over time using the data collected. So see how this makes sense? During a snowstorm, snow fell at a constant rate. That's this piece right here. Then it stopped snowing. That's this piece right here. Then it started snowing at a different rate. That's this piece right here. Okay? And here's a good question. A lot of people, we will be learning in this chapter about y-intercepts. A y-intercept is where your graph touches the y-axis. And a lot of times people are like, why do you always talk about the y-intercept? Like, who cares? It's just something I'm supposed to memorize. I mean, people aren't rude or anything, but they'll be like, why is the y-intercept such a big deal, right? The y-intercept very oftentimes gives you your initial condition. So notice how in the problem, they didn't tell us there were 3 inches of snow on the ground. That's not stated in the problem, is it? But I can tell by looking at the graph, at time 0, there were 3 inches of snow on the ground. So we already know information that was not told to us in words, but we can pick that up from looking at this. That can be helpful. How much snow was on the ground when the snowstorm started? 3 inches. And we get that right. Okay, let's try another one. So this one's a little different. One spring day, let me try to get it centered on here. One spring day, Taylor noted the time of day and temperature in degrees Fahrenheit. During the day, the temperature rose, stayed steady, and fell at different rates. On the set of axes below, Taylor created a graph of temperature over time. Okay. This is good. So again, let's orient ourselves on our graph. It looks like the x-axis is time. So anything that has to do with time passing, we know we're moving left and right. Temperature is vertical. So anything to do with temperature, that's changed vertically. Okay, we kind of understand what we're looking at now. All right, so what is the question? What was the temperature at 8 a.m.? Okay, 8 a.m., that's a time. I know I've been given a time, and I also know that time is my horizontal axis. So then I have to find that. Okay, well, let's see. Here's 6 a.m., 7 a.m., 8 a.m. would be right here. So if I go up, that means my graph should be, what, 56 degrees? Because that's my y right here, 56. So let's see. There we go. So see how that works? See how you can go both directions with the questions? You can create a graph given some information. You can interpret from the graph given a graph and get information from it, right? You want to be able to do both of those. Okay? Are we comfortable with those? I know my algebra class, my other algebra class had a little bit of trouble, but I think what they were kind of confused. I know the big question that I kept getting in that class on these graph stories was always the coming back part. So you just have to realize when you come back, you're changing the direction, right? Let's see if I can get you let's see, let's just submit it. Oops. Let's just make something up and it'll tell. I think it'll show me if I do it wrong. Okay, so see how we've got, oh, this one doesn't have any coming back. That's the problem. But just remember from the video I did, remember how the one we did earlier, the line was coming down? That's, I think, what was confusing people is once you start coming back home, your distance is decreasing again. So just pay attention to when the turnaround happens in that problem. What are we, about 15 minutes? Okay. So that's your graphs in general, just your basic graphs. What you're going to go through and do is those basic graphing, right? Okay, then we've got things like, then we've got basically how to graph lines. And it goes from starting very basic to getting more complex. By the time we get to the end, some of you will be able to just look at the equation of a graph. If it's in the right form, you'll look at it and you'll just be able to visualize in your head what the graph looks like. You'll go, oh yeah, has a y-intercept of 3 and a slope of 2. Okay, I can visualize what that looks like. Okay, so it's nice to have some of these more advanced methods. Okay, so graph the following features. A y-intercept. So remember that. What did I say a y-intercept was? A y-intercept is where the graph that you're graphing intersects with the y-axis. So the y-axis, remember, is this vertical one. So this is saying our graph intercepts it at -4. So we go to -4. I'm going to put a point there. Okay, so now what? Now it's saying slope 4. What is slope? We haven't talked about that yet. What is slope? Okay, well, let's look at that. Slope is basically a measure of how steep your line is. So remember, if I go back here and I've got this, see how this is a really steep line, right? And this is not a very steep line. And this line is horizontal. It's not even steep at all, right? Well, the way we measure that steepness, we call it slope, which makes sense, right? And so all these lines that you're seeing me put out here right now, they all have different slopes because they all have different steepness. Now, this line right here, without even calculating it, I know that this line right here has a positive slope because it's increasing. This right here has a negative slope because it's decreasing. Just if you want to keep it straight, would you rather have your bank account look like, in fact, let's do this. Let's get rid of this. If you were going to sign on to your bank account and look online and come up with a graph of your bank account, would you rather have it look like this, or would you rather have it look like this? Which one would you rather have? What would be the preferred graph for your bank account? We'd rather have this, right? Because this means that as time's going on, your number of dollars is increasing, whereas over here, your number of dollars is decreasing and you're about to hit 0. That's not good, right? So just think of it that way. Increasing slope, if it's a bank account, if your bank account is increasing slope, this would be decreasing, negative, negative slope. The slope we're also going to frequently refer to as the rate of change. And the rate of change, do you want a positive rate of change on your bank account, or do you want a negative rate of change? Do you want the change to be positive, going up, or do you want the bank account to be negative, getting less each day? You want it going up. You want something like this, right? Or you want it really steep. I want it growing really, really fast, right? So that has a larger slope. It's steeper, okay? So how do we measure something like that? How would I measure the slope between 2 points? Let's do an example. 4, 1 and 1, 3. Okay, so what would be the slope? Yeah, that works. How would I figure out the slope of the line that goes through these 2 points? Well, it turns out we have a formula for that. It's called the slope formula. So we oftentimes will use the letter M. So in this chapter, whenever you see the letter M, that means slope. We usually don't use, sometimes people do, I think it's bad form. Some people use M as a variable. Sometimes it's fine. But if you're dealing with lines, a lot of times people are going to think M is your slope, and it just gets confusing. So we usually reserve that. Here's your formula that you need. All right, this is your slope formula. Y2 minus Y1 over X2 minus, why didn't it compile there? X1. That's your slope formula. I'm sure many of you have seen this before. Probably looks familiar. It's easy to remember. It's just your change in Y's over your change in X. Some people remember it as rise over run, because when you change your vertical, that's a change in your rising. Horizontal, like when you run, you don't run vertically. You don't run up the side of a wall, right? Even like you see people do parkour. They're not just running indefinitely up the side of the wall. They kind of jump off of it. So when you run, you don't run vertically. You run horizontally. And then, right? So we can even write that. Let's make this equals rise over run. Okay. So how do we apply that to our problem? And what is Y1 versus Y2? Just pick your points, call one of them point 1, call one of them point 2. And I find, like, when I do these problems, I label them X1, Y1, X2, Y2, and then you're not going to mix them up. So let's take our 2 points. What were they? 4, 1, and 1, 3. So let's take our 2 points here. 4, 1. And 1, 3. Well, generally I would call that. And it doesn't matter, but I'm just going to call the one I have listed first, I'm going to call that X1, or 0.1. So the points would be X1, Y1. That little subscript just means they're from the first point, right? Oops, I didn't use a comma here. That just means they're from the first point, and then the ones from the second point. So, if I say this is X2, that means the X value from point 2. So this would be X2, comma, Y2. Okay, so 4 is my X1, 1 is my Y1, 1 is my X2, and 3 is my Y2. So now all we do is we just plug them into this formula. So in fact, let's just copy this so everyone can see what I did. equal sign, and then we're going to get, so now I'm just going to plug things in. So y2 is 3 minus y1, which is 1. 3 minus 1. X2 is 1 minus 4. And then, of course, we want to simplify things when we can. Why not? Right? Like, there's really no good reason not to simplify stuff. So what that's going to be, 3 minus 1 is 2. 1 minus 4 is negative 3. And you can put the negative in top or bottom. It doesn't really matter. So we end up with negative 2/3. That negative will pop up right here. You could write it as 2 over negative 3, but some teachers aren't going to like it when you write negatives in the denominator. So I just try not to do that because you might have teachers later who get grumpy about it. This means to get from one point to another, you move vertically in the -2. You move vertically -2 units and positive horizontally 3 units. So let's see if that's right. So to get from here to here, we'd go down 1, 2, and over 3. 1, 2, 3. Sure enough, gets you right there. So the line that goes through this has a slope of negative 2/3. Okay, that's how we would categorize the slope of that line. So anytime you're given 2 points, you just plug it into the slope formula. There you have your slope. It's straightforward. Okay, so you get that slope right there. So let's go back to our problem we were working on. Because here it said we have a y-intercept of -4, so that means, oops, we don't want that. We want it down here at -4. And a slope of 4. What is a slope of 4? Well, 4 really means 4 over 1, right? If we want to write that as a fraction. So what does that mean? I go up 4, 1, because rise over run. So 1, 2, 3, 4, and over 1. So that should be my line. Let's see. There we go. Right here they even have it. 4 over 1, rise over run, up 4, right 1. Create your line. There you go. You're good to go. Okay? So that's how you do that one. Let's see. I can't really start any of these topics in 5 minutes, so we will pick up with these next time. Feel free to bring questions, right? If you bring questions, then I know, oh, students have this question, and we can start off with that. But we'll look at these next time, okay? Are there any questions? No questions? Okay, then if that's the case, I'm going to shut down the YouTube stream. Anyone who wants to, either if you're already in Zoom or you want to get into Zoom and ask me questions, feel free to do so. Otherwise, I'll see you in a couple days. All right, thanks, everybody.